this afternoon is Francois Morain, who will talk about modular curves of a number fields in ECM.
Okay, thank you, John. Thank you for to the organizers for the meeting. Except next time, do something about your heels. Anyway, so you see, this is factoring integers. No. So my talk is in the pre-quantum factorization era, meaning we want to factor large numbers. Maybe you know that large means greater than 55. So this is a picture look of a graphical view, artistic view of quantum computing. First, you need a cat, because you cannot do quantum stuff without a cat. And second, I will not kill it, or half kill it, or whatever. Just two things about this. So imagine a world in which you put an integer in a box, and at the same time, it is prime and composite. That's nightmare, this for me. Okay, and second, John was reminding us of first answer. And during the first answer, there was an invited talk by Peter Shore that looked like science fiction at the day. Still looking at science fiction, but so it was 1994. Ooh, yeah. So this is supposed, quantum stuff is supposed to destroy usual arithmetic, okay? Which is a bad thing, as you might imagine, at least for old people like me. Up to the point that there is this lingering question: do we need to teach factoring algorithms to young students, or will it disappear with the quantum mechanics? So we can discuss that at length after. Okay, so in the pre-quantum era, there are some algorithms that factor integers, by definition. So just I list all of them. There are not so many. Okay, that's life. So this is a very crude description. I don't need to look at it just for historical context. And in fact, we spend a lot of time breaking numbers, like record numbers, big numbers, interesting numbers, and of course, not RSA keys. And there's a second context in which we need to test a lot of small numbers. Okay, and depending on what you want exactly, you use one of the methods I present. Yeah, the third thing I should add to my introduction was the fact that I counted only 2 papers about factoring in ARTS this year. So this tells you something about difficulty, interest, and so on. Anyway, okay, so the first things that were done was just looking at properties of integers, say over Z or Q, certain methods, and then starting with NFS, we started to look at the use of algebraic number theory to factor integers. So in NFS, you look for a nice extension field related to your number, in which maybe the arithmetic, yeah. Sorry, but anyway. Ben Smith always told me you should do 16/9 ratio when you do slides. So I did it, and now, okay. Okay, and so with the starting point is Cunningham numbers, powers of small integers plus or minus 1. and with an obvious cyclotomic field construction and many interesting properties. And so we could do the same thing. I mean, we can do the same thing with elliptic curves and factorization. So this is one of the ideas of my talk. Okay, what is an elliptic curve? This is very brief. You know that it's a cubic equation with a smooth curve and blah, blah, blah. And you have tangent and chord method, which enables you to add 2 points on a curve. And you have a group law with algebraic equations, easy to program, and so on and so on. So the theory for fields is easy. For rings, you have to be careful. You can do that in a proper way. There are many results and the maps and whatever, how many people, complete laws, whatever. Or you can do that in a sloppy way. You imagine your curve that we define very basically like this, more the composite integer n, for which the so-called discriminant of the curve should be invertible. And when you add 2 points, here I choose the projective law, you add 2 points. And if you find at some point that the z coordinate is not prime to n, then you have found a factor of n. And if it's not the case, the use of these laws of the result is that you have the reduction of all points mod p add up correctly mod p for all primes divided. So we have interesting set, and we can perform operations. So we can do factorization. Okay, so basically what you do is you compute here factorial j times p0, and you wait for the third component here to have non-trivial GCD with n. And it works when you have the luck that some prime divisor of n leads to the reduction of E mod P to be smooth. So sorry, the cardinality of the reduction is smooth. It divides some big composite number P. And the difference with preceding methods is that by Hass's theorem, you know that the cardinality of E of Fp is close to P, but varying with coefficients of P. So if you use a lot of curves, one of the cardinalities in the interval here should be J smooth, and then you factor n. This is the really basic algorithm. So let's call it ECM plane. You do something weird, which is construct an elliptic curve at random. You can just do it this way in Weierstrass form. And when you add everything, let's show that conjecturally, the method should find a prime divisor P of n in a sub-exponential time in P, and not in n, as for normal. And here you have some coefficients here. So sorry, the average running time is here with x replaced by P. So this is sub-exponential with this constant here. But at the same time, it is proven that you need a lot of elliptic curves to be tried before finding the prime factor P. Okay, so actual factoring began very soon after the announcement of Hendrik-Lenstra. So it was announced in February 85. And first factors were found quite rapidly, presumably by Peter Montgomery at the end of the day. And many things were tried, like finding good equations, fast addition laws. You see a list. The first to do that were the Chudovsky's brothers, Peter Montgomery, more recently Edwards, plus any form of twisted, projective, whatever Edwards form. And there are also different models by Coel depending on the torsion points. And there are also algorithmic improvements to speed up the evaluation of all our quantities, fast polynomial arithmetic, and the reference implementation, which is GMP ECM by Paul Zimmer. Okay. So what can we do to find good elliptic curves? I mean, I have to define what good means and why they should exist. So there is this theorem that tells you that the structure of an elliptic curve over a finite field is a product of two subgroups, isomorphic, blah, blah, to two subgroups, the order of 1 dividing M2, so the second number of points, and also P minus 1. And this is the consequence of the very theory. Okay, so the idea, what really matters? The maximal order of a point is M2. So why not try to have M2 small? Or M1 big? Still satisfied with. Difficult to imagine. Or maybe we can force M2 to have a given divisor D. And the moral of everything is that a smaller number is more easily smooth than a large number. Okay, following. And maybe we can do better. So what was done was find good elliptic curves over Q and later over K, having a large torsion group. Perhaps find an infinite family of this, and perhaps an infinite family with a point of infinite order. So we don't insist on that. Okay, so what is a good curve? So it took some time to define properly what a good curve can be. So this is based on first ideas by Montgomery, and then more recently by Bulescu and co-authors. You see, what you're interested in is this quantity here. A good curve should be a curve with a high value of its expected value of Lx valuation. Okay, L is, of course, a prime number, like P. You compute the cardinality of Fp, and you look at the valuation of this cardinality mod L. And basically, the larger this quantity, the better. It should tell you that then the cardinality of F mod P should be smoother, more smooth. Okay, you can formalize this like saying, okay, it's probability that your cardinality is B smooth. B smooth means all prime factors are below B. Should be the same as an integer of size n times e to the power alpha of e being B smooth, with alpha e defined by this quantity. So there's an analogy with number fit case and leading to this formula. Okay, so if you look at this, you see that this guy should be negative. And if this guy is negative, then it's much better. I mean, this number, this cardinality here, behaves like a smaller number. This is the idea of this data. And we can show using sales results on torsion points on curves over Q. But in fact, this quantity of E is always finite. And it has a global minimum, which is given by this quantity here. Depends on the representation and so on. It's okay. It's not mine. So why not trying to sorry, that's stupid, should be less than minus 8. Otherwise, you see this is contradictory here. So this should be way around. So new families are appeared from that. You see one with a -3 instead of this, and there are more curves by these guys. And in fact, if you want to decrease alpha, then one way to do that is to have many small rational L to the k torsion points for you. And this is what was done for Q. And give some detail about extension feet. So what is a modular curve? Basically, it parameterizes curves, elliptic curves over K, having a torsion group containing this guy with M1 divisible, dividing into some. So here are the curves for genus 0, and curves here for genus 1. And for genus 1, I put them in transform, and many more curves can be found in those tables. And the tables here are exact, contrary to a lot of the curves in the literature. I spent a long time correcting formulas before I discovered those tables. For me, computations maybe. So you can ask, why is it that I can claim these are the only curves with alpha genus 0 and 1? So there it depends on very high-level theorems. First one by measure, who tells you that the possible torsion groups for an elliptic curve are scarce, and they are all given in these lines here. Okay, we know how to build them, and blah, blah, blah. For the number field, it's even worse. Okay, if E over K has degree D, and it has a point of order P, then P is bounded by this quantity, which depends only on the degree, not on the P. Okay, so this is very hard. And this theorem by Merel was extended by Parent to give you a bound on P here. So you see, this is a uniform conjecture, telling you that you cannot dream. You cannot have torsion points of large value. If we knew how to do that, we could factor integers more rapidly with ECM. We cannot. Anyway, what happens for quadratic fields? You see, there's a small list of possible torsion groups, but this answers the question: if K is quadratic, in which list can I find the torsion groups? It doesn't answer the precise question: is given K, what is the possible torsion groups? Okay, over group, this is the same question over number field system. And there are Galois properties and whatever properties, which means that the situation becomes kind of zoo, not completely done, and there are many papers still being written. Okay. So just to give you an example, I took the last two families for x1 of 4.8 and x1 of 2.12 in Edwards form, just for fun. What this means is that I can use these curves, and if I can reduce them mod P, then their cardinality are divisible by 32. Okay, now I do everything together. So the theory tells you something like, for a given number field K such that x1 sin mod, in K as rank, as non-zero rank, and generator G, you compute a lot of curves related to x1. So kg is a point, from this point, you can deduce an elliptic curve, which has torsion group Z1 cross ZL. Okay, if you have luck, you can use the Simmons program to compute the rank of this guy here and hope for a non-zero rank and a generator, and then you can plug it in ECM. Okay, so this is too sketchy. The reason is that KG has a height which goes to infinity very rapid. And I don't know what is the precise complexity of the Simmons program, but it explodes. I mean, it will take forever. Okay, so this is a path. Can we improve this program to handle more and more cases? I know this is not easy. There are specialists in this room, but will tell me it's impossible. But anyway, I asked a question. So what I can do instead is, in fact, see this mod n directly, state mod n, and build up the curve I need for doing ECM with technicalities and so on. Okay, so let's go back to the definition of a good curve. So I just told you that you take a point, blah, 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 blah. So we already did this a long time ago for k equal q. And now I have to explain how to measure what I gain. So here it's a bit hand-waving again, because I don't know anything about torsion points on elliptic curves or high degree number fields. But let's say that my field K is Galois of degree D, and then I replace alpha L of E by this quantity, which is close to 1, which I already defined, with the following rationale. You see, I look only at primes that splits in K. Okay, this means that the minimal polynomial of K has D roots, or P. Okay, so I take my curve, which is defined over K, and then I reduce it mod each of the prime factors. Each time I get a curve defined over FP, and I compute this valuation, the F valuation of the cardinality. And so when I do ECM, I don't know on which curve I will land. So the obvious thing is say, okay, I will average these quantities, meaning that I take the D values, I divide by T. Okay. So this is a bit, maybe not completely true, but probably give some hints about what should happen. So example, take x1 of 11, that's this equation, and from this you can build elliptic curves having 11 torsion points with these formulas here. Okay, you need formulas to go from x1 to the actual curve having this torsion point. So these are simple formulas for that case. I consider q of square root of 6 and x1 of 11 over q of square root of 6 as rank 1 and generator given by this formula. And this was found by the Simmons program. Here it's easy because quantities are small. And now I can compute also the relevant value of alpha with my preceding formula, and I find something like a -3 point blah blah. So what can I do with this curve? I can try to factor them. So sorry, to factor numbers b to 6n plus or minus 1 with this curve. Okay. Statistics for alpha. You see, I take these big values of M1 and M2, and I looked at some polynomials defining number fields, and they are generally related to cyclotomic fields or quadratic fields. It's much easier. K is the K for iterating G. And you see pretty good values of alpha. Okay, with a strong bias with cyclotomic fields, which I don't completely understand. But I can make it work for a cyclotomic field, but any subfield, in fact, will do. So in fact, starting from a field, you look at all of the subfields, and all the subfields can be looked at with respect to X1, and we look at generators and so on. So find points, be careful, CM curves have to be avoided because their reduction properties are very special. You can try to see something like take an automorphism of K, then if E has rank 1, then it will be the case for sigma of E. It can be useful, except if E and sigma E are isomorphic or even isogenous. And then isogenous curves happen or occur, because you see, if I'm looking over quadratic fields, this is a good way to build two curves because they are all defined over polyquadratic fields. So if I'm not very cautious, then I will hit isogenous curves, and there's something stupid by using two isogenous curves in ECM. You lose your time. And you can detect them. If K is Galois, it's not difficult. And in the case where you try to use it for non-Galois case, then you use this lengthy paper by John and Nashman. Okay. An algorithm to discover isogenous curves. Last thing, if you it's very rare that you find points of infinite order. So what you do is infinite order. So I claim you can use this trick, starting from an elliptic curve, and you putting this quantity here. I can build a point x01 on a twist of E lambda. Okay. And so when you reduce it mod P, either you have luck and you end up on the correct curve mod P, or you end up on the twist, which might not be what you were looking for. And this is the same problem as happens in using the P+1 method. One of the ancestors of all this. So many more details are in the paper. Of course, I have to show you big factorizations. You see, I took this example, which is a subfield of Q of zeta 67, generator, blah, 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 blah. And you see examples. Torsion is Z2 cross Z12. And you have factorization of the order. And here I had luck, maybe, let's say, because you see the subgroup is exactly what I said. So this is not always the case. So you see here everything is okay. And these are two cases where I did not land on the curve I was expecting, but rather on the twist. At the twist, made this move order. You have to order. Right. So it works when factoring stuff. Of course, only for bizarre numbers here, but I mean. Okay, so is it a really important and wealthy path? I don't know. I told you that we know almost everything on torsion points on Q bar, and the objects are getting bigger and bigger. So that's not completely obvious. I still wait for some generalization of the work of Pauli. This more properly defined value of alpha, and that's all